Hello, this is Team Full Custom. We were part of the EEC119 class this quarter with Dr. Raj. We did the home automation IC project. My name is Kevin Kampen.
Tim Andreas.
Alex Solorzano.
And Ryan Chiang. So our project was the home automation project. The guidelines that we were given at the beginning of the quarter was basically we had to design an IC that had analog and digital parts. So it was very broad and vague. And we decided to go with the home automation project because home automation is a hot topic right now. A lot of people are getting smart devices, and so we wanted to make a controller for the house that would turn a home into a smart home. The way we do that is we do a master and slave configuration while communicating along the power line that's already built into the house. So the master and the slaves are put into different rooms in the house. The master is in a centralized room while the slaves are in any other room throughout the house, and there can be up to 16 slaves. The master controls all the slaves while also taking inputs from the house. It takes in light, temperature, and motion sensing, and so do the slaves. And then we have them communicate along the power line that's already built in. So the master device, as I mentioned, it takes in temperature, motion sensing, and interior lighting. We turn the analog information into digital. It also takes in the temperatures from the other 16 rooms, and then it computes the average. We do some temperature controlling and send a desired temperature to the thermostat to change the temperature in the room. We also have a Wi-Fi input from a user through something such as a smartphone, and the user would send in data that can be stored into the RAM and be sent along to the master and slave devices. In the slaves, we have inputs for temperature, motion sensing, interior lighting, and then we do some control to control the room lights that's dimmable. We can send our temperature to the master, and we can control the air vents. The desired temperature that comes in from the master is also sent and stored into the RAM. So now I'm going to talk about my part of the project. This is our Cadence Design of the top level, so you can see one master and up to 16 slaves. So if we go inside here, each of these is a chip that has a regulator, which is what I worked on. And my regulator basically takes in 120 volt sinusoidal signal from the wall of the house with a frequency of 60 Hertz, goes through a 15:1 transformer, and that goes through to my regulator. In my regulator I've got a full bridge rectifier, an active regulator, and a compensation regulator that are in parallel. The full bridge rectifier just turns the AC signal into a DC signal that is supplying my regulators, and then the regulators are supplying a 1.5 volts supply to the rest of the chip. And so the active regulator is always on, while the compensation regulator is only on when there's enough current being drawn from the load that the supply voltage drops to a limit that I've set, and then the logic here will turn on through these up converters and control these logic gates to turn on the compensation regulator as necessary. As far as the design of my regulator goes, I've got a bias circuit that generates the reference current, and then I've got a op amp with a gain of 52 dBs, or a little less than 450 gain, and a phase margin of 73 degrees. So my bias circuit, I use current mirrors. It's a temperature independent current mirror that sets the current going into the op amp, and for the op amp I'm just using a single stage, so I get good phase margin, it's very stable, and I did not need a ton of gain for this. And that's the basic configuration of my op amp. Next we're going to have Tim talk about his PLC and control logic.
Okay, my name is Tim. I designed the powerline communications module of this chip. So the scheme I employed was frequency shift keying, which encodes digital data as a sequence of pulses of varying frequency. This is so the resulting tones can be superimposed onto the existing power lines within the house. In order to simplify access to the shared communication medium, the communication is arranged as a master-slave configuration, in which the master module is responsible for initiating communications and requesting data from the slaves spread throughout the house, while the slaves are only responsible for monitoring the power line and responding to the request for data. So this state machine is simply a controller that allows this master-slave type configuration. Then there are two more circuits that I want to talk about. First, there's a couple circuits for transmission of bits and a more substantial data path for receiving and decoding of bits. So first we have a simple multiple input shift register that receives 1 byte 8 bits of data from the higher level control and shifts each bit out one at a time to the tone generator, where the corresponding tone for each digital bit is generated. And the tone generator is simply a programmable resettable counter that generates tones of two different frequencies divided down from the global clock frequency. Now, the first circuit on the receiving data path, we have a simple 4-bit flash ADC that samples the incoming waveform and converts it to a digital format. Second, we have a 12th order finite impulse response filter that filters the digitized data to determine whether the received waveform corresponds to a digital 1 or a digital 0. Then the output of this bandpass filter is sent to a peak detector, which essentially improves the noise rejection of the filter by rejecting any spurious spikes in the filter output. Finally, the filter data is loaded into a 8-bit shift register, which is then passed out to the higher level control. So this is an overview of the power line communications module.
Alright, this is Ryan, and I'm going to talk about the light control. And the light control is basically just a PWM controller that uses exponential values. So the reason we use exponential values that are stored in here in this ROM is because we want a linear output with a linear input, and since the eyes perceive the change in brightness at a logarithmic rate, we want to store exponential values so that we can get a linear output. So in the ROM here, it's a 10 by 26 bit ROM, and all the bit lines here are just always pulled high until you select a level that pulls a certain bit line low. So excluding this first line here, which is just a 0, you can see that these values here are exponentially increasing. So the first row here, the lowest brightness level has a pulse width of 10 ones, and the highest has a pulse width of 24 ones, and then the rest here are just zeros. So looking here in this brightness select, which is basically just the row select, this is how you can change, or you can choose the different brightness levels, and it's basically just a bidirectional shift register that goes up and down basically if you press up or down, and here's just more control logic for that and the reset. And then the output is just a simple shift register, 26-bit shift register, and basically it just takes in a new value whenever you select a new row, or it will, if you're just on the same row, then it will just continually shift that that output over and over again. And then in the output, you can just take a look at one of these pins, and then you'll get a PWM signal because you're just continually shifting. And then, so since we want the the user to see the different changes in brightness, we want this clock here, or this frequency here, for the level selector to be really low. So this here is a 2 Hz signal going into this block, and to get that signal, we divide a 6 Hz signal coming from the PLC by 2 to the 5th, so 32 clock divider, and the output shift register needs to run at a higher frequency so that you can see the lights with no flickering. So in order to get a 120 Hz signal out here, we need a 3 kilohertz signal here, which is divided by a divided 200 kilohertz signal from the PLC. And these clock dividers here are the same. They're both 2N clock dividers. So we just have a half adder and a flip flop, and every one of these stages divides the previous clock by 2. So here we have a 2 to the 6 or a 64 clock divider.
I'm Alex, and I'll be talking about the dual slope ADC for our chip. I decided to go with a dual slope ADC because we just needed 8 bits, and we have a 9th bit for the sign bit. We were not that concerned for precision or speed, so I did not go with SAR or Delta Sig. The way the dual slope ADC works is it has 2 voltages, a reference voltage and an input voltage. The reference voltage is the complete opposite of the input voltage. All my comparators and circuits are compared with respect to virtual ground, which is our VDD over 2. The main component in this circuit is the integrator, which is just consists of a 2-stage differential pair op amp, which has a gain of 2000 and a phase margin of around 100. I have 2 comparators, which are just inverter chains with the V mid to be VDD over 2. And then I have my counter logic, which converts the actual analog input to a digital output. As I said before, the comparators just consist of inverter chains with the mid voltage being at VDD over 2, and I took advantage of this instead of designing an actual comparator, because the inverter is just going to give me a 1 or a 0 depending if it's above VDD over 2 or below, which is what I want. This comparator is the odd comparator, which is just the odd number of inverter chains to get the opposite voltage of the input voltage. This counter logic consists of half adders and D flip-flop registers. The first set of registers just counts from 0 to 255, so 8 bits, while the second set of registers hold the actual converted data. And the reason I did this is because I wanted to make the second set of register independent of the internal reset that my first pair of registers do. This is just a simple overview of my ADC. And over here we have the overall layout for the chip, which has the SRAM, the ADCs, the LDO, the PLC, the controller logic, and the PWM. The area size is about some micrometers squared long, and the inside is not that big. This is a 20-pin I/O chip, which has some extra pads for VDD and ground. We also did our poster for the Senior Design Showcase, which we just described our circuit in detail about the master level, top level, slave, the cost analysis, the design features, and the goals for our circuit. The cost, as we figured out in the cost analysis, the chips will cost around $4, which is a affordable solutions for homeowners to buy our modules instead of upgrading their house to be a smart home. And depending on what type of devices they have, we can integrate our circuit to communicate with those devices. And that's basically our home automation project. I would like to acknowledge Dr. Raj and our TA Scott Block, and also the School of Engineering for giving us this chance to design our own chip.